And on the first day, God said, "Let there be light." And there was light. I probably can imagine how many times you have heard that passage from the Bible and moved on to the next from Genesis. But in this chapter, we're going to dive in and learn more about light and talk about what exactly is light and what are some of the properties of light and what does the word quantized mean? So that's what I hope to do in this video short here is talk about the 3 different properties of light, tell you about and explain the electromagnetic spectrum. We'll talk a little bit about photons and explain what is meant when it says, when you hear that light is quantized. All right, so first we start off with the 3 properties of light. 2 of these properties are unique to each different type of light, and 1 is constant for all types of light. I would imagine that most of you are familiar or have played with at some point in your lifetime one of these prisms, which you can just take some white light or from the sun and place a prism in the vicinity of the sunbeam or in the beam of light, and out on the other side you see a rainbow of colors. And this is separating white light into the visible spectrum. So you actually are able to see red light, orange light, yellow light, green light, blue light, and purple light. We have this small quick anagram, Roy G. Biv, to help us remember the order of the colors of the rainbow. Red light is different than purple light, obviously, because we see 2 different colors with it. So, and out of these 3 properties, wavelength, frequency, and speed, red and purple differ amongst 2 of these, but red light and purple light have the exact same of one of these properties. So let's talk about what these properties are. Usually when we scientists think about light, we say that light is like waves. So we draw these wave-like structures of light. Okay? They have peaks and they have valleys, or sometimes these are referred to as troughs. The wavelength of light is the distance between the peaks of the wave. Okay, so here I've got this little black line with these black tick marks is a time line or a time scale, and I've got this red light coming through. Okay, and red light has a wavelength that is this distance, whatever that is, I'm not sure. In contrast to purple light, notice it also is wave-like, but off the bat, you can kind of see there's something different between red light and purple light. And hopefully you see that it actually has a different wavelength, right? The wavelength from peak to peak of purple is a lot shorter than it is from red. So wavelengths are unique to the different types of light. And this goes beyond just talking about colored light. And I'll explain more when we talk about the electromagnetic spectrum. What is frequency? So when you hear the word frequency as a scientist, now all I think of is how often, what's the frequency of it occurring? And that essentially is what frequency is here. Frequency is the number of cycles the wave goes up and down per second. So frequency has the units of per second, and it counts how many complete waves you get for every 1 second. What do you see as the difference between the frequencies of red and purple light? Which one do you think has the higher frequency? Do you think that there are more complete waves in purple light per second than there are in red? I mean, again, consider these black lines right here with the ticks. Those are our time points. So you would be correct in saying that purple light has a higher frequency than red light, right? We get more cycles for every 1 second as compared to red light. So wavelength and frequency are going to be different for all types of light, all types. But there is one constant among all types of light, and that would be the speed of light, how fast light travels. So when we talk about the speed of light, usually we're referring to the speed of light when it's in a vacuum. And a vacuum is just a container that has no gas particles in it whatsoever. Space is actually a massive vacuum, all right? So the speed of light in a vacuum is 2.99792 times 10 to the 8 meters per second, okay? However, when light is traveling on Earth, it's traveling through air. And the difference between a vacuum and air is that air contains a lot of particles. We know that air is mostly nitrogen gas. So you've got gas particles, you've got oxygen particles, you've got particulate matter, right? Soot, things in our atmosphere. So actually the speed of light in the air around Earth, inside Earth, travels a little bit slower. It travels at 2.99705 times 10 to the 8th meter per second. Given that very tiny difference between light traveling in a vacuum where there's nothing and light traveling in air within the Earth's atmosphere, we just go ahead and say that light travels at 3.00 times 10 to the 8th meters a second. Okay, we're rounding, but notice that technically we're not lying if we use this constant. So all light travels at a constant rate of 3 times 10 to the 8th meters per second. There is a handy dandy formula that you can use that links together the speed of light and frequency and wavelength. And let's switch to pen real quick. And that equation is that the speed of light is equal to the wavelength times the frequency of that light. So if we looked at the units of this, speed of light is in meters per second. Wavelength is a distance, so that's in meters. And frequency is in units of per second. Or you could say 1/second, right? It's per every second. So if you were to multiply these two together, those two units, you see that you get meters per second. So the one cool thing that I absolutely love about chemistry and math processes in chemistry is that units are always going to work in your favor. If your units are messed up, then the math's not right. So I would always suggest writing your units down when you're working sample problems. So let's use this equation and work a sample problem from the book. This is the Your Turn 3.3, and it just says, what is the frequency in hertz? And hertz is Hz, and that is per second. So you could say second to the -1, you can say 1/second. That's another way you can say what hertz is, but hertz is in units of per second. So what's the frequency in hertz of green light with a wavelength of 525 nanometers? So 525, oops, pretend I didn't write that right there, sorry, 525 nanometers. Okay. Remember that nanometers, let's draw my other M right here. That's nanometers. Geez, I gotta get a board that works a little quicker, huh? All right, nano means something, right? That's a prefix, and it's not 525 meters, it's nanometers, and nanometers are really, 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 really tiny. So nano is times 10 to the -9. All right, so I could write this another way, which is how I would suggest you start thinking about things, especially if you work sample problems in about light. I would call this 525 E -9 meters. My 9 didn't really show up, did it? 9. E -9 meters. Okay, so that's the wavelength. So I can plug wavelength in up here. The question was asking me for the frequency in hertz, which is per second. And remember, speed of light is constant for all types of light. Green light, red light, IR light, UV light, X-ray light, radio waves. They all travel at the same speed. They only differ in the wavelength and frequency. Okay, but anyways, so if I plug in 529 for my lambda, remember what is the numerical value of the speed of light? It is 3e8 meters per second. 3e8. See if that got it. 3e8 meters per second is equal to, so the speed of light equals the wavelength of light times frequency, v, or nu, it's Greek nu. So if I want to solve for frequency, what do I need to do is I need to divide both sides by the wavelength of light. So 525 e -9 meters Oh, it's gone off the page. All right, well, we'll just have to use our handy dandy calculator, but you can see what I'm doing here. I'm going to divide the wavelength from this side and this side, and that'll leave me with frequency equals in my final answer, honestly. So, got your calculator here, ding, 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 ding. Remember about that EE button, it's like your best friend, EE. So I'm gonna type in 3EE8, and it gives me my 3EE8, oh, sorry for the glare. And now I divide it by 525 EE, there's my E again, -9. So I'm going to type 9 and then the negative. And so you make sure that it says -9 there, and then I hit enter, and I get 5.7 times 10 to the 14th. So the hertz, hertz is equal to 5.7 times 10 to the 14. Oof, times 10 to the 14. That is murky. I'll fix that too. So, but that is the frequency of green light. So we talked about the three properties of light: wavelength, frequency, and speed. Remember, speed's constant for all types of light, and wavelength and frequency vary. So let's talk about what these different types of light are. It's a spectrum that we call the electromagnetic spectrum, and this is kind of what it looks like. So here is this axis here that is in wavelength. Remember, that's again the distance between peak to peak between all the waves, the wave of light. So the main ones, the main different types of light that are most common, it's grouped. We have radio waves, right? The radio is light, technically. We're all most familiar likely with this visible light because we see color on a daily basis. But there are definitely different types of light. Radio is a form of light. If you ever used a microwave in your dorm room to heat up your food, yep, you were playing with light. It just has a different wavelength. In your microwave, the wavelength of light is about 1 centimeter. That's about 1/3 the distance of this knuckle digit on your thumb. So if you look at your thumb real quick and go, oh man, 1/3, that's the wavelength of the microwave light that's used in your microwave to heat it up. After microwave, then we have IR for infrared. If you look at the visible spectrum, you have purple on this side or violet on this side and red towards this side. Infrared is always by the red, and UV's on the other side of visible, and this stands for ultraviolet. Look, here's violet. Makes a lot of sense. But what is the IR light used for? So IR light is used for your Bluetooth technology. It's how your cell phone and your headphones communicate to one another. Remotes, remote control cars. For kids or your TV remote, those all use infrared light to send the signal from the device to the receiver. So either from the remote to your TV or from the controller to the car. Then we're again all familiar with visible. And let's make a few notes about visible light. Red is a lower energy. So radio waves are very low energy, right? If you got bombarded with a radio wave, you're not gonna fizzle up and blow up or anything, right? But like if you look at the kind of down here on this closer side of the spectrum, you've got X-rays and gamma rays, and hopefully you're aware that you shouldn't get an X-ray every day of your life because that could cause some severe damage to your cells. So we try to limit the amount of X-rays we get, and gamma rays would actually obliterate your body and you just disappear, like in that one scene of Joe Dirt when they like light off the big firework and he looks over at his friend and his friend just like disappears from the bottom up. Yeah, that would be what it would be like if gamma rays were a thing. So these are all high energy, like very high energy, very low energy, radio and microwaves. So red light is closer to the micro and radio wave. So that red light is lower in energy than purple light. Okay, purple light is higher energy. So if you look at the nanometer distance, the visible light ranges from 400 to 700 nanometers, 700 being red, 400 being purple. So the nanometers, you also get bigger. So 700 nanometers is bigger, right? The wavelength is bigger than in the purple. And we saw that back a couple slides ago, right? The wavelength of red was bigger, was longer than the wavelength for purple. Okay, sorry. So visible light there. Okay, so UV light is mostly, we get a lot of that from the sun that penetrates in through our atmosphere. Thankfully, the ozone layer sucks up and sops up a lot of UV light before it can hit us, but some of it does make its way through, and that's why we need to wear our sunscreen. Stay tuned to all those other videos, and you'll learn a little bit more about the chemistry behind it. Then we have X-rays. Okay, probably at some point in your life you've had an X-ray. I know I've had my fair share. And like I said, gamma rays are the smallest in nanometers in wavelength. And this is an image of a nuclei, so protons and neutrons and atomic nuclei, and this is a gamma ray. It's about the size of an atomic nucleus, which is why if that light hit that atom, it would spread the atom's nucleus apart, and you would just be like, I don't even know what it would look like, but you would just vaporize. All right, so that's the electromagnetic spectrum. Remember, high energy, gamma rays are high energy, really low wavelength, high frequency. So high energy, high frequency, low energy, low frequency on the opposite end over here with radio. Okay. And wavelength, it kind of runs opposite to that. So very small wavelengths are gamma rays, very large wavelengths are radio waves. In fact, some radio waves have a wavelength that's the size of a football field. So imagine sitting at the 50-yard line of a football field, look left, look right, you get that whole football field. That's the entire peak to peak of a radio wave, you know, bustling through the air above you. Okay, so whoop, large wavelength, low energy, low frequency, small wavelength, high frequency, high energy is gamma. And then everything is in between, you know, it's in between. All right, so since this chapter focuses on radiation from the sun, radiation is another word for light from the sun. The sun gives off mostly IR, visible, and UV light. So IR helps heat up our atmosphere to keep it temperate. The visible light is what we help see with, so we can see everything. And then the UV light is unfortunately not a good thing for us, which again is why we need to take precautions to protect ourselves from the UV light that makes its way through our atmosphere. Again, keep in mind, stay tuned when you watch the ozone layer videos, because the ozone layer helps us from this UV light. Okay, light sometimes, so what are photons? Photons are the word that scientists use to describe particles of light. Wait a minute, Dr. Hughes, I thought you just were telling me light's a wave, light's a wave, light's a wave. Well, light is a wave. And in fact, if you were to break that one wave apart, you would see that it has it's two waves oscillating in the electric field and in a magnetic field, hence electromagnetic spectrum. I'm not going to ask you a million questions on that. But anyways, it's a wave. But light also acts like a particle. Although light has no mass, write that one down. Light has no mass. It is kind of just pure energy coming through. And it has particle-like characteristics and wave-like characteristics. So we come across this nature of light that is particle and wave-like, and we've called it the wave-particle duality of light. Okay, so think of light existing in these photons, little particles of light, but maybe think of them traveling in waves. Okay, so it has both wave-like properties and particle-like properties. But the crazy thing is these particles don't have mass, right? It's just energy. Thank you, God, for that energy. He created light on the first day. He created all energy on the first day. Crazy stuff. All right, last thing to talk about is light is quantized. Whoa, what does that mean? That sounds like such a crazy word. There are two ways that light could exist. It could be continuous light or it could be quantized light. So if we think about the electromagnetic spectrum, right, gamma rays all the way over to radio waves, that looks like it's a continuous spectrum of light. However, it is not. So continuous would mean that, let's say if you were to roll this ball down this slope, it would just continually roll down. And it would hit, you know, if let's say you had a distance here, you say this is 10 feet and this is 0 feet, this ball would hit 10 feet, 9.9999, 9.99998, 9.99997, 9.99996. This is a continuous, okay, right? It's continuous spectrum. Okay? Quantized, though, is more like stair stepping. So those, like, all those little tiny nuances between 10 foot and 9 foot don't exist. It's like you're at 10, then guess what? You drop down to 9. You don't go to 9.2 or 9.21 or 9.1117. That's more of the continuous spectrum. They're just like whole number jumps. So 10 to 9 to 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1 to 0, period. So that's what quantized light means. So back on the electromagnetic spectrum, when we talk about wavelengths, wavelengths only exist in whole numbers. You don't see wavelength 529.3333721. That does not exist. It's just wavelength 529, period. That's it. And that's the difference between a continuous and quantized. So light is quantized. When we get to the video about me explaining how fireworks work, I had drawn this small energy diagram to show how the electrons in some of the metal centers are going to jump into higher energy states. And so this, again, just to kind of visualize continuous versus quantized light. So here on my y-axis, I've got increasing energy going from essentially 0 up until whatever I want it to, infinity. And if energy was continuous, then you would just have this big block right here, okay? But energy is quantized, and so instead of having a continuous block, you see you have these like steps of energy. So energy only exists at, 0 joules. A unit for energy is joules. So at 0 joules, maybe 150 joules, 200 joules, and maybe 220 joules, right? Instead of being continuous, which is just like from 0, everything in between 0 and 220. So you'll see me draw this quantized energy diagram a little bit later. Hopefully that sums it up for y'all. We covered the 3 properties of light. We talked about the electromagnetic spectrum. We said that light has both wave and particle-like nature, hence the wave-particle duality of light. And I explained that light is quantized. So enjoy the rest of the Hughes views, y'all.